All right, so this is our objective project for 350 lab. Looking at this beginning circuit here, we have the part 5 of the lab where we have an input coming into a PWM generator that is going into a feedback loop, but right now it's deactivated. Going into our motor that we've chosen from Morg, we've chosen the brushed motor of D1125B1. And inside here, we could look at the different arrangements inside the motor that we have changed and edited for our purpose. We have the gear ratio set to 16, and we have a inertial load working at 10 grams per centimeter squared. We are not using an unbalanced load because when we were to introduce it into the system, it would cause MATLAB to freak out and not work, and we would have issues. And I didn't want to go through the debug process of getting it working. It was easier to get a inertia load working in the beginning. Using what we have here is the encoder from Lab 5 that we were told to use in the demo. Going into the HFS. The HFS is going into the decoder, which our decoder is just a quadrature shaft decoder that we have here. Thank you, MATLAB. Going into a feedback loop that has a pole. Our HFS needs some sort of transition from giving us positional data and translating that into a pole and a zero for our feedback that could be returned to our system right here at the PWM cycle, and then we can send it into our motor. So what this circuit looks like now when we turn it on would be this shape. As you can see, it consistently changing, and it's going to hit a point where it did a full revolution and then start changing in the other direction. That's fine. Now let's add in the feedback. Inside this feedback, we have, let's run it real quick. Look at the ramp up like we desired. And then it's going to taper off and then sprint back up into space. You can see that it's trying to go to its target location of 0.5 because that's our input. And then afterwards it goes into unknown territory. It's gone. So I would say our overshoot is pretty high and the system's not that stable. Now, to change this, we can add in a PID controller. Our PID controller is quite simple. We did a very simplistic design. Looking inside of it, we could see that we're using the three different inputs for the PID, the 1/s, the general gain, and the derivative. Each of these are set through a fine tune to get the desired output response that we have been looking for. So using this current test and new parameters, we are going to run the system. And we see that it goes up, doesn't hit 0.6, and then tapers off like that. So it looks like to me that the settling time is around 6 or so. The percent overshoot is quite low, probably under 20 to 15%. If we were to try to adjust even more and fine tune the PID controller, we would lose our settling time. And so we've decided to prioritize the settling time a little bit over the percent overshoot. And that being said, we can play with it real quick. If we decrease the gain by 25 to 75, we can get a different response we can get a worsen overshoot response, but a increased settling time of just before 6. So 5.5 seconds for our settling time, and an increase of time, or the same time peak, but increased peak percent overshoot. And that's not what we want. So we can go back and adjust that back to 100. Well, we can play with the system a little bit more. Let's leave it at 75. 75. Okay. And let's increase this to 60. And let's increase this one to 60. And when we run the system, get our initial shoot up, goes a little bit over past, the percent overshoot's quite high, and then looks like settling time isn't at 5. It's a little bit past the 7-second mark, so it looks like it's still unstable. So that's why we've tuned it to these specific values of around 75 for the main gang, and then the 2 KP and KDs are tied together. Finally, we could add in a integrator to remove all the error in the system, which will should transform the system into a linear system and make it just a straight line, producing no error. As it goes off to infinity, we could adjust the system. I'll wait until the time equals 100%. So we're ready to adjust. Adjusting it, you see it's nice and linear. It goes one point to the other pretty linearly, and it's what we expect when we add in a integrator to change the system to type 0 to type 1, and it gets rid of all the errors, and this is the output that we have acquired. With that being said, Robert, are you ready for your portion?
I would if my mic was on correctly. All right, so I'm ready. Just stop the screen share.
Okay.
All right, so screen sharing my screen 2. Is that showing up correctly? I hope it is. So
Yeah, it shows up correctly.
Okay, so for lab 6, the root locus, what we're doing is taking the K and then the following blocks and putting them into a system. Going with the MATLAB portion first, we set the K, block 1, block 2, block 3, put them all together, throw them into the SISO tool, and then we find our nice pretty step response. So the first thing we do is just figure out where the poles are. So at the bottom, we'll see that it's at negative 1.26 plus 3.4 on the imaginary axis. So the first thing we were to do was find 20% overshoot and adjust to there. So due to being zoomed out too much, it will make it difficult to adjust the overshoot. So we zoom in, grab a hold of it, and adjust it down to about 20%. I don't like how MATLAB zooms in like that, but it is what it is. So now we see that we changed from our previous location to 1.34 to 2.6 on the imaginary axis. But that changed it to the 20% overshoot we were looking for. And that's nice, fun, and dandy. So now we want to change the gain for part 2. Once again, we zoom in on the root locus to get the nice precision we want. With the arrow function, grab that. And now we are decreasing the root locus once again. Slowly, we overshot. So 0.7, which is close to 0.707 we want, but if we zoom in even more, I wish MATLAB was better for adjusting like this, but That's what it is. All right, so now at dampening, we'll find that our current location, negative 1.43, with 1.43 on the imaginary axis. The theta value, of course, being, if we zoom out some, if we think about it in the trigonomic idea, it's at a 45-degree angle from the origin, 0.707. Who would have thunk? All right, so now moving to part 3, we want to adjust this to where it's marginally stable. In that case, we would want to move it where the initial value is close to 0. So this is a little bit more complicated, but we'll figure it out because we're great students like that. And we're not that great. Okay, that works. So moving from the real to 0 to negative real to 0, you see that the amplitude, well, there we go. See, let's get a better fit though. Zoom in here. So we see that it's marginally stable, and I wish it wouldn't auto. No, get rid of this thing. That's probably the root of our issues, not root locus. Haha, funny joke. Let's see, delete current data type. All right. And if we zoom in closer, because at a certain point when you get close to 0, and we were able to zoom out, all right. Well, that's best we do, but the closer it gets to 0, it acts normally, but once we overshoot, you notice that if MATLAB was better to work with, there we go. Once it gets past the axis, then it is no longer stable. Thus, keeping it to 0 is where we have the marginally stable. All right. Now, let's add in a 0 for part 4, which is the SISO tool. Let's return this into a more normal state. Okay. And let's adjust the poles to something a lot more stable. That's easier for us to visualize. All right, this might, nope, it doesn't help. All right, that works good enough. So we see standard amplitude and gain. All right. So now let us actually add a 0 to the root locus. In this case, we will add it to the other side of the far pole. And then here we see that it adjusts the root locus, so it takes a little bit longer to go to the unstable region, but it doesn't curve out as much as it used to. Now when we pull it farther away from the pole, we see that the instability region extends out more, but then inversely, when we bring it closer, in fact, let's bring it to the other side. Oh, no. Let me zoom in. So let's take this pole and move it to the other side. We see that it could no longer go unstable, thus stabilizing the entire formula. And the closer we bring it, the more it stabilizes until it breaks like that. All right, so then let's delete that. Bring our roots back here. All right, so we now see our transient response. Now let's add a pole. First, we will add it on this side. Why do we do that? So it makes a second root locus. Now, in doing that, we could extend it, and we see it changes the root locus values. And at the same time, if we get closer, the transient response pretty much is relatively stable. Now let's bring it to the other side. And it does pretty much the same thing. But the biggest change is the addition of this secondary curve. Right. And then we see from the poles when we adjust them, as long as we stay within the stable region, the response time always happens to be around 6-7 seconds, showing that the response is how we want it to be. All right, and that's it for lab 6.
All right, I hope you like our presentation.